Welcome back. In this lecture we will see some more generalizations that can be arrived at using the basic axioms of probability. So first we will review the axiomatic theory of probability. We have a random experiment and there is a sample space corresponding to it. The objective is to assign a measure called probability to each event A, call it as P of A, such that A gives the precise measure for the chances that A will occur. So to this end we first construct a sigma algebra, which is a class of events or subsets of the sample space which is closed under the set union and set complementation operation. Okay, so for any event A which is a subset of the sample space omega, the first axiom tells that the probability measure for the event A is a number which is greater than or equal to 0. Then, as we already saw, that the sample space itself has to be an element within the sigma algebra, and its probability measure is assigned a value of 1. That is the second axiom. In the third axiom, what we will do, we will generalize the idea that if there are two events A1 and A2 which are disjoint, then the probability measure of their union is the sum of the probability measures of A1 and A2. That result can be generalized for an infinite collection of disjoint events. Let A1, A2, A3 and so on is an infinite collection of disjoint events. Then the probability measure of the union of those finite or infinite collection of disjoint events is the sum of the probability measures. Okay, then we will prove a theorem, that is the probability measure of the impossible event or the null set is 0. During this we will do it using a different reasoning. First we saw that the P of psi is 0 can be arrived at as follows. First let us consider a collection of infinite number of disjoint events. Okay, A1, A2, A3 are all different disjoint events that can be defined in the sigma algebra. Then we know that psi intersection psi is psi, that is the intersection of two disjoint event is also a disjoint event. So we have a collection of disjoint events, okay, collection of null sets or impossible events which are all disjoint. So union of AI will again turn out to be psi. So then if you, from axiom 3, this gives that the probability measure of this set psi is the sum of the probability measures of AIs which are individually disjoint. So we have this relation P psi is equal to sigma P psi, and this can happen only when P psi is equal to 0, given the fact that all probability measures are non-negative numbers. Then we can also arrive at one more result, that to a finite collection of disjoint events, if you want to find the probability measure of union of them, we can append to them any number of or even infinite collection of null sets without affecting the total probability measure. That is, what we do is, let A1 to AK are disjoint events. To that we append an infinite collection of events AK1, AK plus K plus 1, K plus 2 and so on. It's actually K plus 2 and so on, which are all disjoints. Then the sequence of events A1 to AK plus 1 and so on are all disjoint among themselves, because disjoint events, impossible events themselves are disjoint, which are again disjoint with any other event A1 to AK. So A intersection psi is equal to psi. So we see that if you take probability of union of I varies from 1 to k, that will be the same as the probability of union of I varies from 1 to infinity ai, because from k plus 1 onwards what we append are all disjoint events. This can be seen, so the probability measure does not get affected by adding more number of null sets or impossible events. That is what they show. This can be proved as follows. So because all ai's here are disjoint, we can write it as sigma I varying from 1 to infinity p of ai, which can be split into two sums, one varying from 1 to k, another varying from k plus 1 to infinity. Then we know that these are all impossible events whose individual probability measures are all zeros. So these are all sigma of zeros, which will not contribute anything to this sum. So we get back this one. So we have proved that to a set of events you can add any number of impossible events without affecting the probability measures. We will see that actually when we deal with real world problems, we may have to encounter infinite number of events, okay, and we have to deal with that. We will look at a simple example to this end. Consider we are testing batteries and look for a battery whose voltage is within some prescribed limit. So what we do is we have a big bag full of batteries. We take one battery after another. Each one is a random experiment. We will call it as sampling. So for a given sample, we look at the voltage level of the battery, and if it is within the prescribed limit, we have a success. Until we get a success, we keep doing the sampling. So the set of all possible events that can occur, you can see that it has infinite, is as cardinality infinity, because we can have the following possible events. Event E1 is the one in which the first draw itself is a success. Event E2 is the one where the first one is a failure followed by a success, and so on. Then we have got two failures followed by a success, and so on. So as such, we can have infinite number of such events that can in principle occur. Okay, so suppose the probability that a particular battery being satisfactory, that is its voltage level is within the prescribed limit, or the probability of success is 0.99, then we can see that probability of E1 is 0.99, whereas probability of E2 is 0.01 into 0.99, because you would see that the two this has got two events which are themselves disjoint, and therefore their probability this we will see it later. Okay, that is, these two are indeed independent random variables. Those probabilities gets multiplied and so on. So P of E2 is given by this, P of E3 is given by this, and so on. So first thing we can see is that all these events are disjoint among themselves. That is, if E1 occurs, E2 will not occur, E3 and all cannot occur. Okay, so they are all disjoint among themselves. Because of that, and collectively all these infinite collection of events will form the sure event S. Okay, so S is E1 intersection, this has to be union, E1 union E2 union E3 and so on. But E1, E2, E3 are themselves disjoint. Therefore, we will see that P of the sure event or sample case omega is equal to 1 is given by P of E1 plus P of E2, P of E3 and so on, which can be written as 0.91 into 1 plus 0.01 and its whole squared and so on. So this actually forms geometric series, and it can also be easily seen that this is of this form, and therefore their sum will, because R, the multiplication factor R is less than 1, it can be written as A by 1 minus R. So we have basically 0.91 divided by 1 minus 0.01, which is equal to 1. So this is a simple case where we may have to encounter infinite collection of events, and we should be able to handle them. Then we have the complement rule, which says that if A is an event whose probability measure is P of A and its complement event A complement is such that P of A is equal to 1 minus P of A complement, or P of A complement is equal to 1 minus P of A, or P of A plus P of A complement add up to 1. So this can be seen as follows. So by definition, what is A complement? It is such that A union A complement is equal to the entire sample space, and A and A complement are disjoint. Therefore, if you take P of A union A complement, their probability measure should add up. So that will be equal to P of A plus P of A complement, and this A union A complement is nothing but the sample space or the Schur event whose probability measure is 1. So we get a result that 1 equal to P of A plus P of A complement, which is what we are looking for. So this is a result which we need not impose it in the axiom, which will also follow. We have only told in our axiom that P of A is greater than or equal to 0. It will also follow for any given event in the sigma algebra. P of A has to be less than or equal to 1. This follows from the previous proposition that 1 equal to P of A plus P of A complement. So this quantity has to be greater than or equal to P of A, because P of A complement takes a value greater than or equal to 0. By dropping this, what we see is that P of A has to be less than or equal to 1. Okay. Then we have this addition rule, which we have already proved previously, but now we can see it using a different line of argument. Take two events A and B, then P of A union B is P of A plus P of B minus P of A intersection B. How? A union B can be written as A union of B intersection A complement. Okay. So A is already included. So you consider A complement and only include those in B which are not in A. So this is a way of rewriting this. The advantage being these two sets are disjoint. So A and B intersection A complement are disjoint. So their probability measures add up. So using the known result, we can write P of A union B is P of A plus P of B intersection A complement, but B itself can be written as sum of two partitions. One is B intersection A, another is B intersection A complement, and B is a union of these two sets which are also disjoint. Okay, so their probability measure should add up. Okay, so because of this one, these two are disjoint. P of B can be written as P of B intersection A plus P of B intersection A complement, which will lead to the fact that any given, suppose we want P of B intersection A complement, it can be written as PB minus P of B intersection A. Okay, so coming back to this one, P of A union B is, okay, as we have seen, P of A union B is P of A plus P of B intersection A complement, which we can write it as P of B minus P of B intersection A. Therefore we have got this result. Well, we'll just look at a simple example. Let us say you have got a residential suburb area wherein 60% of all the households get internet service from a local cable company. 80% get television service from that company, and 50% get both the internet as well as the television service from that service provider. So the question that we may would like to answer is, if you randomly choose an household, what is the probability that it gets at least one of the two services from the company? And another question is, what is the probability that it gets exactly one service from the company? So what do? We formalize it. Let us define an event A, which is the event that a chosen household gets internet service from the cable company. B is an event that an household gets television service from that company. Then, as given here, P of A is 0.6 and P of B is 0.8 and P of A intersection B, that is getting both services, is 0.5. Once we have these numbers, we can use the addition rule that tells P of A union B is PA plus PB minus P of A intersection B. That gives us that 0.6 plus 0.8 minus 0.5, that is 0.9. So this is at least one service. Now you look for the answer for the second problem, that is an household probability that an household gets exactly one service. So again, we diagrammatically illustrate that the event A union B can be split into two events. One is the event A and another is the event A complement intersection B. So using this, we can always find out the probability measure of these two are disjoint events. So the probability measure of A complementary intersection B is P of A union B minus P of A. Okay. So what we know is that probability of getting exactly one service is P of A intersection B complement and P of A complement intersection B. That is, in this whole figure, we should only remove this part, that is A intersection B. We should include this part and this part, which is what we have done here. Individually, these two can be calculated. Okay, how? P of A union B, which we know as 0.9 previously, is PA plus P of A intersection B, and putting the value of 0.6 for this, we can get that P of A intersection B is 0.9 minus 0.6, which is 0.3. In a similar manner, P of A intersection B complement can be written as follows. That lead to 0.1. Therefore, probability of getting exactly one service is this 0.1 plus 0.3. So that is what is given here. Okay, we have three partition of P of A union B, and individual probabilities can be found out. Then some more results is that if A is an event which is a subset of event B, then P of A has to be less than or equal to P of B. Then it also follows that P of A union B is always less than or equal to PA plus PB. Okay, then we already saw how we can generalize the formula for P of A union B to three sets, like A union B union C, or to even more set. Now we will derive it in a slightly different using line of reasoning. Okay, so that is why we carry out this exercise. So given an event A union B union C, we can always write it as a sequence as follows. This can be written as, see, three disjoint events. One is A, another is A complement intersection B, another is A complement intersection B complement intersection C. So all three are disjoint and mutually disjoint, but collectively they will give you this one. Therefore their probability measures add up. So this is equal to PA plus P of A intersection B plus P of A intersection A complement intersection B complement intersection C. Indeed, we can generalize it to 4, which is being shown here. P of A union B union C union D is PA plus P of A complement intersection B plus P of A complement intersection B complement intersection C plus P of A complement intersection B complement intersection C complement intersection D, and so on. So this way of writing, okay, allows us to use one of the third axiom quickly and derive new results. Let us do this for this particular one. So we have written A union B union C in this manner. Now we will go on to further write it as this is P of A plus P of B minus P of A intersection B. This is PC. Now you look at this, okay. A complement intersection B complement intersection C, okay. So so this can be written as, okay, see here what we are doing is basically, if you look at this one, A complement intersection B complement intersection C, okay, is being rewritten as P of C minus of P of A complement intersection B complement whole complement intersection C. So this third term here is rewritten as this term, okay. Now if you apply a De Morgan's law, this becomes A union B, and then if you apply a distributive law, you will get this P of A intersection C union of B intersection C. Now we can rewrite this as collect PA, PB, PC, and then A intersection B, and then this will be, can again be written as this form, okay, and then this is nothing but A intersection B intersection C. So this basically is being used to illustrate that this is a way in which any given union set of a number of unions can be split, okay, and this is another powerful law that we can apply more often to simplify expressions, okay. Now we will see what is called as the inclusion exclusion principle, okay. I'll just try to reduce it, okay. So here we see that this, we can try to get an intuitive feeling of why this has to be true. That is, you will see that any given 3 sets within the sample case can take this form. So what we do in order to get the probability measure for union of all these things, we add the probability measure for A, B and C in the first 3 terms. Then in each of this one, we are adding these intersections, A intersection B intersection C and so on, twice, okay. In order to remove that, okay, the overadding of these intersection taken 2 at a time, we subtract these, okay, this one. But in doing so, this, what we did is we added it 3 times when we are adding ABC, and we are subtracting it 3 times when we are subtracting these intersection here. In effect, we never accounted for it. So in order to account for it, we add it once more here. So this is a way of understanding this whole formula, and now we can even generalize it and come up with the inclusion exclusion property. This property holds good for even if you look at the set theory and if you want to find the cardinality of union of sets, and this is shown the inclusion exclusion principle for the set theory. The same thing holds good if instead of cardinality, if you take the probability measure. That is, union of I varying from 1 to n ai is nothing but the cardinality of this set is nothing but sigma I varying from 1 to n cardinality of ai and minus taken 2 at a time, intersections of the set taken 2 at a time, plus taken 3 at a time, and so on. Okay, so instead of this cardinality, we can put probability measures and we will get the corresponding theorem. Then the generalized De Morgan's law is something that we have already looked at. Union of I varying from 1 to n ei whole complement means individually we have to do intersection of the complement events. Similarly, intersection of I varying from 1 to n ei whole complement will make the union of these complement events to be we have to find the union of them. Okay, and for the same thing we can also apply the probability measure for this one. This Boole's inequality, okay, okay, is nothing but what we are doing is this is a quick way of finding the upper bound for the union of any number of sets. Okay, that is, if you only take the first order term in the inclusion exclusion equation, we get the Boole's inequality. So this is something which you have already proved, okay, in the previous lecture. Quickly going through it. So what we are showing here is probability of A intersection B is always greater than or equal to this quantity. We can rewrite it in this form. We will show how it can be done. 1 minus P of A complement is P of A and P of B complement is 1 minus P of B. So rewriting, we get it's PA plus PB minus 1. Okay, so if you take P of A union B, it has to be less than or equal to 1. So expanding it, we get PA plus PB minus P of A intersection B is less than or equal to 1. Taking 1 to this side and P of A intersection B to other side, we get this equation, which is nothing but the Boole's inequality, holding good for these two things. Okay, then we looked at the sum of the sets, okay, that is union of n sets ai, I varying from 1 to n, can be split into the following things. The probability of union of I varying from 1 to n ai can be written as a sequence in which taken one at a time, if you call it as the set, their sums as set S1, and the sum of probability measures of sets taken two at a time but only distinct pairs, that we will call it as S2. Then S3 will be taken 3 at a time, distinct triples, and so on. Then we can define such, split them into sums of this form. We can easily see that P of I varying from 1 to n ai, okay, will be, if you want, the actual value will be equal to j varying from 1 to n, if you replace it by n, and minus 1 power j minus 1 into sj. Okay, that is, it's all the sum of these one with alternating plus and minus sign. Okay, we can see it is minus 1 power j minus 1, because if you look at S2, okay, then you will see that will have a minus sign. 2 minus 1, it will have a minus sign. The S3 will have a plus sign, which will also follow from it. So it is an alternating plus and minus. So what here we show is, if this sum of S1 plus S2 to all the way to Sn will be equal to this quantity, but if we truncate it at any given k, then for certain values of k, which is odd k, okay, this measure, okay, this value will be more than the actual value, if k is equal to even, then this value will be less than this, the actual value. So that is what this relationship tells. Okay, yeah, so which we have already emphasized it in the last lecture also. Thank you.